AI chatbot you have used has a dirty secret. It is answering from what it memorized during training, not from facts, not from documents, not from anything it can point to. Just patterns it absorbed during training. And that means it can be wrong, confidently wrong, with no way for you to check. There is a technique that fixes this. It is called Retrieval-Augmented Generation, or RAG for short. RAG gives a language model something it never had before, the ability to look things up before it speaks. That one shift, retrieve first, then generate, is the reason RAG now powers AI search engines like Perplexity, enterprise copilots, document chatbots, legal assistants, AI agents, and thousands of knowledge-based AI tools. But RAG is not a single feature, it is an entire system, with moving parts, design trade-offs, and failure modes. In this video, we will break down how that system actually works, step by step. Today, large language models are impressive. They can write, summarize, translate, reason, generate code, and even build entire applications. But here is something most people do not think about. Ask ChatGPT to summarize your latest meeting notes, and it cannot because it has never seen them. Ask it about your team's project status, your internal policies, or what changed in last week's product update. It still cannot help because none of that data exists inside the model. It sounds helpful, but it is guessing. Why? Because the model is frozen in time. It only knows what it learned during training. Your private data is completely invisible to it. And when the model does not know something, instead of saying, "I don't know," it invents an answer and delivers it with total confidence. This is called hallucination, and it is one of the hardest problems in AI. The core tension is this. A large language model is excellent at generating language, but generating language is not the same as knowing the truth. So if we want AI that answers from real knowledge, not just pattern matching, we need to connect the model to external information at the moment it generates a response. That is exactly what RAG does. RAG stands for Retrieval-Augmented Generation. The name is technical, but the concept is not. Before the model writes an answer, the system searches for relevant information first. It pulls that information into the prompt. Then the model generates a response grounded in what it just retrieved. Think of it this way. Without RAG, the model has to answer using only what it picked up during training. With RAG, you hand it the relevant data sources first and ask it to answer based on those. The model still writes the final response. But now it has evidence, not just intuition. This is why RAG powers AI search, document Q&A, enterprise copilots, and knowledge assistants. The generation is still the model's job, but the facts now come from real sources, not from training data alone. At a high level, a RAG system moves through 5 stages. Prepare the knowledge, retrieve relevant chunks, rank and select the best evidence, augment the prompt with that evidence, generate a grounded answer. The flow looks like this: user question, search, relevant documents, context injection, LLM generation, final answer, often with citations attached so the user can verify the source. That is the skeleton. Now, let's open each bone. For retrieval can work, the system needs a knowledge base to search. This could be PDFs, web pages, internal wikis, product manuals, database records, meeting transcripts, code repositories, support tickets, any source of truth your organization cares about. But raw documents are messy. They are too long, too varied, and too noisy to pass directly into a language model's context window. So the first step is preparation. Clean, parse, and split documents into smaller pieces called chunks. A chunk might be a paragraph, a section heading with its body, or a few hundred tokens of running text. Why break them up? Because retrieval works best when it can pinpoint a small, relevant fragment, not wade through an entire 50-page report. And the chunk size is a real trade-off. Too large, you drag in noise. Too small, you cut off the context that gives the words meaning. It sounds like a minor detail, but how you size your chunks quietly shapes the quality of every answer the system will ever give. Once you have chunks, you need a way to search them, not by keywords, but by meaning. This is where embeddings come in. An embedding model converts a piece of text into a vector, a list of numbers that captures its semantic meaning. You can think of it as coordinates in a high-dimensional space where similar ideas cluster together. So a chunk about refund policy lands close to a chunk about return process, even though the exact words are completely different. That is the power of semantic search. You are no longer matching strings. You are matching meaning. Every chunk gets embedded and stored in a vector database. The knowledge base is now indexed by meaning and ready to be searched. Then comes the moment that triggers everything. A user asks a question. Say, what is our refund policy for enterprise customers? The system embeds that question and searches the vector database for semantically similar chunks. It might pull back a section from the refund policy, a paragraph from the enterprise contract template, a customer support FAQ entry, and a recent policy update memo. Notice, the system is not answering yet, it is gathering evidence. This distinction matters. RAG does not make the model smarter, it gives the model better input. And the quality of the final answer depends almost entirely on whether retrieval finds the right information. If the wrong chunks come back, even the most powerful model can only produce a weak answer. Get retrieval wrong and nothing downstream can save you. Retrieval rarely returns a clean, perfect set of chunks. Some results are highly relevant. Others are tangentially related, outdated, duplicated, or noisy. So a strong RAG system adds a ranking step, a second pass that rescores and filters the retrieved chunks before they reach the model. This can be done with a cross-encoder re-ranker, hybrid search that combines vector similarity with keyword matching, or metadata filters that enforce constraints like document type, department, recency, or access permissions. Think of it as a judgment call. Retrieval casts a wide net. Ranking decides what actually deserves to be in the prompt. This step is critical because the model can only reason over the context it receives. Feed it the wrong evidence and it will confidently generate the wrong answer. Now the system has a curated set of high-quality chunks. The next step is to inject them into the prompt, right alongside the user's question and a set of instructions. A typical augmented prompt looks something like, "You are a helpful assistant. Answer the user's question using only the following context." If the answer is not in the context, say you don't know. Then the retrieved chunks, then the user's question. This is the augmented part of Retrieval-Augmented Generation. The prompt now carries external knowledge the model could never reach on its own. And prompt design still matters here. The instructions shape the model's behavior. Should it summarize or quote directly? Should it include citations? Should it refuse to answer if evidence is insufficient? These choices determine whether the system is merely fluent or genuinely reliable. Finally, the LLM generates its response, but now it is grounded. The answer is based on the documents in the context, not just internal weights. Without RAG, the LLM might say, "Our refund policy is probably 30 days." With RAG, it can say, "According to the enterprise refund policy, eligible customers may request a refund within 30 days of purchase, subject to the conditions in Section 3, and link to the source document." A guess versus a claim you can trace back to its source. That is the whole point. RAG does not eliminate hallucination completely, but it gives the LLM evidence to work with. That is the difference between a fluent response and a trustworthy one. A grounded answer is already a big step. But RAG gives you one more thing, a way to verify the answer for yourself. This mechanism has a name, citations. So how does a citation work? It comes from something we set up earlier. Remember that every chunk was stored with metadata, which document it came from, the page, the section. That source tag never gets thrown away. It rides along with the chunk through retrieval and into the prompt. So when the model writes a sentence using a chunk, the system already knows exactly where that chunk came from. It attaches that source back to the claim. That link, from a sentence in the answer back to the original passage, is the citation. And that one link changes everything. The AI answer stops being a black box. It becomes something you can inspect. The system says, "This policy applies only to enterprise customers." You click the citation. You land on the exact paragraph it came from. You confirm or challenge the claim. This matters most in high-stakes domains, such as legal research, financial analysis, healthcare guidance, regulatory compliance, and enterprise knowledge systems. In these contexts, the question is never just, can the AI produce a nice answer? The question is, can I trace where this answer came from? Citations do not guarantee correctness, but they turn a claim you have to trust into a claim you can check. And that is what separates a toy demo from a production system. Let's ground this in real products. Perplexity uses RAG to search the web, retrieve sources, rank evidence, generate an answer, and show inline citations, all in seconds. Enterprise copilots use RAG to connect language models to internal documents. HR policies, project plans, product specs, Knowledge bases. Employees ask questions in natural language and get answers drawn from company data. Customer support systems use RAG to retrieve the latest troubleshooting guide or warranty terms before generating a response. So the answer reflects current policy, not stale training data. Legal and compliance platforms use RAG to search across contracts, regulations, and case law, surfacing relevant clauses instead of forcing lawyers to read thousands of pages. Developer tools use RAG to let engineers query large code bases and API documentation conversationally. Different industries, different data, different interfaces, but underneath the same architecture you have just seen, running quietly inside the tools millions of people already rely on. RAG is powerful, but it is not bulletproof. If retrieval misses the right document, the model answers without the evidence it needs. If chunks are poorly sized, critical context gets lost or buried in noise. If ranking is weak, the best evidence never reaches the prompt. If documents are stale, the answer inherits that staleness. If the prompt instructions are vague, the model may ignore the context or overstate what the evidence supports. And here is the hardest failure mode. When the knowledge base simply does not contain the answer, the system should say, "I don't know." But many RAG systems still struggle with graceful abstention. They generate something plausible instead of admitting uncertainty. The takeaway is this: RAG improves grounding, but it does not guarantee truth. Every link in the chain, documents, chunking, embeddings, retrieval, ranking, prompting, evaluation, has to work well for the system to be reliable. Production RAG is an engineering discipline, not a prompt trick. Here's the simplest way to hold RAG in your head. A language model answering alone is like a person working from memory. They may know a lot, but they can forget, they can be outdated, and they can make things up. A RAG system is like handing that person a search engine and a stack of highlighted notes before they answer. They still write the response, but now they have something real to reference: retrieve, augment, generate. 3 words, 1 architecture. And that single shift from answering on memory to answering on evidence is why RAG sits at the center of so much of modern AI. It is not magic. It is a well-engineered pipeline. And now that you understand how it works, you are not just watching these systems from the outside. You have what you need to build them. Systems that are not just fluent, but trustworthy. That's it for today. Like and subscribe so you don't miss out on more AI deep dives. See you in the next one.